Okay, so we're going over, we have an exam this Wednesday. I will be posting it at 6 o'clock. I'm sorry, at 6 o'clock on Wednesday under the files. Then you have 2 hours to download the exam, preferably print the exam, and then take a picture, do the exam, and then print the exam. I'm sorry, scan the exam and send it back to me. So by 8 o'clock on Wednesday afternoon, I expect the exam back in my email. Um, you are allowed to use your notes. You're allowed to use your book. Please don't Google. Right, you're allowed. You're and or ask people for help. This should be on your own, what you know, but you are allowed to use your notes. There's a lot of vocabulary that you may not be comfortable with. So one of the things I recommend that you do is that you read your textbook, get comfortable with the vocabulary, practice some problems, and that's what I'm going to do for you today. Is I'm going to go over some of the vocabulary, some of the results that you're going to need, and some problems. Okay. So we started here in back in chapter 3. Um, and we were talking about the with 3 people and the lone divider method. And so we have Alan, Brady, Cody, and Diane are sharing a cake valued at $20 using the lone divider method. The divider divides the cake into 4 slices, S1, S2, S3, and S4. Since there are 4 people, the divider needs to divide the cake into 4 slices. Table 319 shows the values of the slices in the eyes of each player. Who was the divider? Okay, so that's part A. And so again, um, you have one person who's going to divide, and the other 3 are going to choose. And we're assuming that the divider is always going to do things rationally so that he doesn't know which slice he's going to end up with. So for him, all of the slices should have the same value. And you could see that for Alan, S1 is worth $4 and S2 is worth $5. Well, he wouldn't have cut it with one slice potentially giving him $4 of value and the other slice potentially giving him 5. He wants the same amount for each slice. So Alan wasn't the divider. Brady, same thing. S1 is 6, S2 is 650. Diane, same thing. S1 is 450. I'm sorry, S1 is $7 and S2 is 450. She couldn't have been the divider. So Cody is the only one who has uh, all the 4 slices valued the same. So who was the divider? And so what I expect you to write is Cody. And what I expect you to say, all slices have same value for Cody. Okay. He's the only one, right? Everybody else, the slices have different value. So if you just say Cody and all slices have same value for Cody, then that's good enough for me. But I do expect you to justify your answer so that you're not just guessing. Find a fair division of the cake. So for Alan, what you might want to do is you might want to make a uh, which um, which slices are fair to Alan. So the cake is worth $20. So he's only a fair share to him. There's 4 of them. Is slices that are worth $5 or more. So S1 is only worth $4. So that's not in Alan's list of fair share. So S2 is, S3 is not, and S4. So for Brady, Brady again wants $5 or more. So S1 and S2. And then Diane. So she'll take S1. And that's it, right? So we want to find a fair division where everybody gets at least their fair share. Some people will be happier than others. Diane is will only take S1. So then, however you want to pair them up, I like, because I've been teaching algebra for so long, I'll pair them up with an ordered pair. Diane has to get S1. And I'll put them in parentheses. Diane gets S1. However you want to tell me, that makes no difference to me. So now that Diane has S1, we move on. Brady will take either S1 or S2, but S1 is not available, so the only thing that's going to make Brady happy now is if Brady gets S2. And now that S2 is not available, Alan is only left with S4. That will make him happy. And so again, but don't forget, you have the divider. And we said Cody was the divider. And then Cody is left with, what's left is S3. S1 goes to Diane, S2 goes to Brady, S4 goes to Alan, and so then all that's left is S3. And there we go. Likewise with all your videos, if you've already started studying, you might want to try the problem before I do the problem, and make sure that you can do the problem on your own. If there's a discrepancy between what I did and what you did, either figure out if one of us is wrong, or you can send me an email and I will look at my response and I will make sure that I didn't make a mistake, and you can send me your work and then I can look over your work. And for some of these problems, there's more than one correct answer. But for this one, there was only one. Oscar, Bert, and Ernie are using the method of sealed bids to divide amongst themselves 4 items they commonly own. Table 325 shows the bids that each of the player makes for each item, right? So find the value of each player's fair share, describe the first settlement, who gets which item, and how much do they pay or get in cash, and then find the surplus after the first settlement is over. Describe the final settlement, who gets which item, and how much they pay or get in cash. Okay, so again, one of the things that we want to do here is we first want to, the problems walking you through is figure out what each person's fair share of all of the items is, right? So item 1 is worth $8,600 to Oscar, plus $3,500 for item 2, plus $2,300 for item 3, and $4,800 for item 4, giving the estate a total value of $19,200. Divided by 3, because there are 3 people in the group, and then he expects a third of that. So for Oscar, his fair share is $6,400. For him to be happy, he needs to walk away with the value of $6,400 or more. For Bert, again, we just add the $5,500 with the $4,200 and the $4,400 and the $2,700. Divide that by 3 and we get $5,600. Now, so for Bert, he thinks this is only worth $5,600, and so he wants a third of that. And so then we get $1,866.67. Ooh, I'm sorry. I made a mistake. So Yes, I had already divided it by 3, and then I divided it by 3 again. So he thinks the fair share is $5,600. This is where things need to make sense, right? I just automatically divided it by 3 again and got 1866. And then I looked over and saw that it was worth $6,400 to Bert. And while they don't have to be the same, you know, it kind of makes sense that they would be close. And the 1866 doesn't make sense, but the $5,600 does, right? So to Bert, his fair share is $5,600. Okay, now finally to Ernie, same thing, $3,700 plus $5,000 plus $3,400 plus $2,300. 14,400. We divide that by 3, $4,800. Okay, so find the value of each player's fair share. That's in the table. And so then I can read that off your table if you make a table, and we're done with that. Describe the first settlement. Who gets which item and how much do they pay for it or get in cash, right? Now, so again, this is just an auction. So item 1 goes to the highest bidder. So Oscar thinks it's worth $8,600. But Bert only thinks it's $5,500, and Ernie thinks it's worth $3,700. So of course Oscar is going to get item 1. Item 2, Oscar thinks it's worth $3,500. Bert thinks it's worth $4,200, and Ernie thinks it's worth $5,000. So Ernie gets item 3. Okay. Item 3. I'm sorry, that was item 2. Item 3, 2,300, 4,400, and 3,400. So Bert likes item 2 most, and so then Bert gets item 3. And then finally item 4, 4,800, 2,700, and 2,300, and so Oscar gets item 4 as well. Okay. So cash. Okay. So Oscar thinks his fair share is 6,400, but Oscar gets $8,600 item and a $4,800 item to him. That's what they're worth to him. So when you take the 8,600 and you add the 4,800, you get 13,400, right? But he's only entitled to 6,400. So we subtract the 6,400 that he's entitled to, and that gives us $7,000 that he has to pay. And since he has to pay it, we make it a negative, and so we get negative 7,000. Okay, so Bert thinks his fair share is 5,600, but Bert gets item 3. But item 3 is only worth $4,400, so he's not happy. He's not getting a $5,600 share. So again, we just take the fair share, the $5,600, and we subtract what he did get, $4,400. And we get $1,200. But because so in order to be made happy, he needs to get $1,200. Okay. And then we move on to Ernie. So Ernie he gets item 2, but item 2 is only worth 5,000, and he thinks, but item 2 is worth 5,000, and he thinks his fair share is 4,800. So you see, he made an extra 200, and so you get minus $200. He has to pay $200, right? So if you add up the minuses, you see that that we collected $7,200. So to calculate the surplus, you add up how much you collected, which is the 7,000 from this person and the 2,000, so the 200 from this person, and so the surplus is you collected $7,200, but you only paid out $1,200, and so then that's $6,000. So you collected an extra $6,000. And so then if you divide that $6,000 by 3, because there's 3 of them, everybody is owed 2,000. So from the surplus, everybody gets 2,000. Describe the final settlement, right? So find the surplus after the first settlement is over. So this is that part right there. There's the surplus. And the next part is to describe the final settlement, right? So just go person by person, right? So Oscar, he gets items 1 and 4 and pays. He originally paid 7,000, but he gets 2,000 back, so he has to pay $5,000 for it. Bert, he gets item 3 and $3,200. And then finally Ernie gets item 2 and $1,800. Notice that we had a large surplus because Oscar thought things were worth a lot more than other people thought they were worth. This first item was $8,600, and the Bart had it at 5,500, and Ernie had it at 3,700. And so the fourth item he thought was 4,800, and the other two had it 2,700 and 2,300. So that's what created such a large surplus. Okay. Okay, so let's continue. Then we came across the method of markers to divide array of discrete items. So 3 players, A, B, and C, are dividing the array of 12 items shown in figure 3 through 34. Use the method of markers. Using the method of markers, the players' bids are indicated in the figure, right? And so first understand what you're being told. So for player A, he's broken up the string of items into 3 equally valued segments. He thinks 1 and 2 and 3, 4, and 7 and 8, 9, and 12 are all equally valued, and he would be happy with any one of those. So that's for A. Player B thinks that he would take 1 through 7, and then 8 and 9, and then 10, 11, and 12. So either one of these three segments would make player 2 happy. And then player 3 thinks that just the first item, or the second through the 8th item, or the 8th through the 12th item. And so the method of sealed markers, what you do is you look from left to right. The first person to get their share is whoever has the first marker first. So the first marker comes right here, right here. That right there is our first marker, and so then C1 is the first one to get his share, and he gets 1. Which items go to C? He gets 1. Okay. Next, we look for the second marker, the first marker that we come across labeled with a 2, right? And so then these two are in a tie, but C is no longer in the running, and so it's just A2. And so then A gets 3 through 7. And then finally, now that A and C are taken care of, B gets the last one, and B gets his third, right? His third interval. So B gets from 10 to 12. When we do that, so that one goes there. A gets 3 through 7. So that means then that 2 is left over. And then B gets 10 through 12. So that means that 8 and 9 are also left over. That is how we do that. So again, get rid of all this, go through it one more time. Scan this from left to right. First marker we see is C1, and so he's the first person that gets his cut, and his cut is everything to the left of that, so he just gets 1. Then we look for the the second marker. The first second marker is A2 and C2, but C's already gotten his cut, so he's done, and so then A gets his second interval, which is 3 through 7. And then we haven't taken care of B, so B doesn't get his first or his second, B gets his third, and so then B gets 10 through 12. And that is it. We move on. Okay. So then we moved on to talk about graphs. We went on to chapter 5. A lot of vocabulary, so we're just going to go through some of that vocabulary in the context of answering some of these questions. So give the vertex set. And so the vertices are just these endpoints here. And so then the vertices are just no particular order, just the letters that are there, A, B, E, C, D, X, Y, and Z. Notice that this graph is not connected. There's no, you have two different components. You have this part of the graph over here and this part of the graph over here. That's totally allowed. It is a graph. And so then B, give the edge list. B, the edge list, right? And so then we have this edge connecting A and B, and it makes no difference whether you call it AB or BA. And then you have this edge joining A and D. So AE. Then you have this edge joining B and D. Then you have this edge joining A and D. And then you have this edge joining E and C. And then you have this edge joining E and D. Going on to the other part, you have the edge that joins X and Y. And all this means is it's a repeated edge. Right? And so you have it again. And typically when we have sets, we don't list the elements more than once, but here we do, just to make sure that we know that we have a double edge. And then we have ZY. Okay. So we have C, give the degree of each vertex. So A, there's A. How many edges are touching it? 1, 2, 3. B, 2. C, 1. D, 2. X, 2. Y, 3. And then Z, just 1. Right. Okay. Give the number of components of the graph. There are 2 components to this graph. And so then finally D, there are 2 components to this graph. It's not a connected graph. It has 2 separate pieces. Okay, so let's move on. Consider the graph in figure 5 through 36. List all the bridges in the graph. So as we saw in the last example, this graph is not connected. One way of looking at a bridge is an edge that if you remove that edge, your graph will no longer be connected. So list all the bridges. If I removed this edge right here, I could still get from any vertex to any other vertex, right? So the graph right now is connected. I can get from any vertex to any other vertex. But if I remove this one, I can still do that. So that's not a bridge. That's not a bridge. Right? You can see that this is a bridge right here. So A, CI is a bridge. Okay. Well, what else is a bridge? Well, anything in here, you have multiple vertices, you have multiple edges, so you're not going to have a bridge. Likewise, that's why you have over here. But over here, if I take out this edge, then you can't get to vertex J. So H, J. So there's not really a algorithm. You just have to look at it and see what edge can I take out and then not be connected, right? And so then by visual, you can see that H, J, and CI are the only ones. Let's move on to B. C. What is the length of the shortest path from E to J? So the length of a path is the number of edges in the path. So we want the shortest path from E to J. And so then you can see that we can just start here at E. We want to get there as quickly as possible. So if I go in either up or down, then I have an extra edge to get to C, at least one extra edge. So why do that? Once I get to C, then there's no choice to keep this as short as possible. I can come straight across to I. If I go up or across, I'm going to increase, well, if I go across, yeah, I'm going to increase the amount of edges that it takes to get to here. And so then why do that? Just go straight across. So going straight across is going to be the shortest path in this case. And so we get E to C, C to I to H, and H to J. And there we go. What is the length of the longest path from I to J? So we want to get from I to J, and we want the longest path. Now, we're not allowed to go backwards. We're not allowed to go to C because then we have to come back. And so then we don't want to do that. I need to get to H. And if I want to take the longest road possible, I don't go straight there because then, that's the shortest. But if I go up and then over and then back down, that's 3. If I just go across and over, that's 2 edges. And so then if I go up, so if I go up and over, that's just another 2. So again, longest, 2, 3, and then 4. And so then it looks like, what is the length? The length is 4. And we go from I to F, from F to G, from G to H, and then from H to J. Ooh, I forgot to describe for C, I described what is the length, right? So from E to C is 1, from C to I is 2, from I to H is 3, 4. So that's also 4. Okay. We have some theorems that are going to be useful and you should know. Euler's circuit is a circuit that passes every edge in a graph, right? And without retracing an edge, right? So if a graph is connected and every vertex is even, then it has an Euler circuit, at least one, usually more. If a graph has any odd vertices, then it does not have an Euler circuit. And if a graph is connected and has exactly 2 odd vertices, then it has an Euler path, at least one, usually more. Any such path must start and end at one of the odd vertices and end at the other one. If a graph has more than 2 odd vertices, then it cannot have an Euler path. So we can tell pretty easily whether we have an Euler path or an Euler circuit. And again, you got to know what those are. An Euler circuit is you're going to cover all of the edges without picking up your pencil and only going through each edge once. An Euler path is you're going to, it's a path, not a circuit. A circuit just begins and ends at the same spot. Okay. So in exercises 29 through 34, choose from one of the following answers and provide a short explanation for your answer using Euler's theorems. The graph has an Euler circuit. B, the graph has an Euler path. C, the graph has neither an Euler path nor an Euler circuit. And the graph may or may not have an Euler path. There is no such graph. Okay. So again, all this depends on how many odd vertices you have. If you have none, then you have an Euler path. If you have exactly 2, then you have an Euler path, and if you have none, you have an Euler circuit. Okay, so the degree of this one is 2. We're good. 1, 2, 3, 4. That one's 4. 4 again. 1, 2, 3, 4. 4 again. 2. 1, 2, 3, 4, 5. Right? So this one has 5. Odd. 2. We're good there. 1, 2. 1, 2, 3, 4. We're good there. 1, 2, 3, 4. 1, 2, 3, 4. 1, 2. 1, 2, 3, 4, 5. Here's another odd. One, two, 1, 2, 3, 4, 5, 6. Even. 1, 2, 3, 4, 5, 6. Even. And that was all of them. I've gone through two odd vertices. I'm sorry, I've gone through all my vertices. 2 of them are odd, so we have an Euler path. Graph has Euler path because of 2 odd vertices. There we go. That's it. So once we know whether we have an Euler path or an Euler circuit, then we want to be able to find them, right? And so Furey's algorithm is really pretty simple for finding an Euler circuit or an Euler path. At each step, if you have a choice, don't choose a bridge of the yet to be traveled part of the graph. However, if you have only one choice, take it. And when you can't travel anymore, the circuit path is complete. In case 1, you will be at the starting vertex. In case 2, you will have, you will end at the other odd vertex. Right? So Furey's algorithm is basically summarized by saying if you have a choice, don't cross a bridge. If you don't have a choice, then you have to cross a bridge. Okay, so find an Euler circuit for the graph in figure 547. Show your answer by labeling the edges 1, 2, 3, 4, and so on in the order in which they are traveled. Okay, so the problem is telling us to find an Euler circuit. I would not ask you to do something that you can't do, so that no need to go through and test that all the vertices are even. They have to all be even in order to find an Euler circuit. Now, what you're supposed to do is you are supposed to make a copy of your graph and then erase the parts that you've already traveled. So I can do that with Paint. Let me go ahead and jump into Paint. Okay, so again, it makes no difference where you start. So I will go ahead and start here. And this is 1. Okay, and so I'm going to start at this vertex here. Oh. and I'm going to erase that right there. And so now I'm here, and I don't have any bridges, right? I can take away any one of these edges and it will not be a bridge, right? So then you can just, if you, that's all you have to do is, yours can be different, it's no big deal. So I'm going to take that one. So then I can now remove this vertex, sorry, this edge. Okay, so now I pick, now I'm here, and now I'm here, and I can take any edge because I don't have any bridges. So then this will be 3, and so then so I'm going in this direction, and so now I come over here and I erase this edge over here. And now here I have no choice. I have to erase this one here. And so now get rid of this one. I don't have to worry about that edge anymore, so that edge is now gone. I mean, so I don't have to worry about that. But now I'm here, right? And I don't have any bridges. So then let me come back and take care of some of the stuff over here. So we'll do 5 there. And so then when we come over here, we erase all this, right? And now I'm here, and I have no choice. This is a bridge because once I erase it, then this edge will, sorry, this vertex will be isolated, but I have no choice. So I have to take it. So that's 6, and then so now I'm here. And if you notice, this is a bridge. If I take this out, this vertex will be isolated, and it's a lot easier to see that I'm over here at this vertex. Then it's a lot easier to see that when you've actually erased it than trying to do it without erasing it. So so that's nice. Okay, so over here then I can't take this one because then I will be isolated. So I can take this one, and so then this will be 7. Okay, but now I have no choice, and I'm over here. The only place I can go is over here. So then this is 8, and I have to erase this one. So now I'm over here at this corner over here. And that corresponds to that one. There are no bridges there, and so then I will go straight down. 9. And then I have to go and erase that because I went straight down. And again, I cannot come over here because then that's a bridge. So I can't cross the bridge. And so then I have my choice of this edge or this edge. I will take care of this edge. Okay, and so then I go and erase this edge, and I'm over here at this corner. And then I will go 11 and 12. Just trying to speed things up here a little bit. That will take care of this one and this one. I did cross bridges, but I didn't have any choice, so that's okay. But now I'm over here in this corner, and no bridges, so I will go right. 13. So then take that out. And again, no bridges. So then I will choose to take this out. That's this one right here, 13. So next is 14. And that takes this one out. And then I'm up here, and now I have no choice. 15. And then I will go up here. So then again I will go 16, 17, no choice. Trying to speed this up. So when I come here I have no choice. Once I get here I have no choice. Here, still don't have any bridges. So I'm sorry, at this point I don't have any bridges. So I can go in whatever direction I want. So then I will do this one, 18. And so now I'm down here. So now I'm over here. But the only thing I can do is go up 18. That then takes care of this one. Not allowed to cross a bridge, so I can't go this way. And there's only one choice now. This way, this way, this way, and back there. So then I'm here. So then this has to... Oh, I'm sorry, this was wrong. That was 18, got me here. Then this is 19. And now I'm here, and I have no choice. 20, 21, 22, 23, and finally 24, and I end up right back where I started. Okay, probably should have blown that up a little bit, made that a little clearer, but that's pretty much the gist of it. Just don't cross any bridges until you have to. Let's come back over here, go to slideshow, from current slide. Okay. So a mail carrier must deliver mail on foot along the streets of the Green Hills subdivision shown in figure 539. The mail carrier must make 2 passes on every block that has houses on both sides of the street, once for each side of the street, but only 1 pass on blocks that have houses on only one side of the street. Draw a graph that models this street routing problem. Okay, and so your vertices in this case are going to be your corners of your blocks. Your edges are going to be the walks he takes, right? Now on this first street that I did, there's only one edge because there's only houses on one side. Likewise here, but here there's houses on both sides, so it's got to take 2 walks, right? And likewise here, and then here there's also 2, and then here there's 2. Here there's only 1. But here there's 2, and then there we go. And so every corner is a vertex, the corner of every block, and an edge is just a walk along delivering the mail. He's only got to walk. He only has to take one pass when there's only houses on one side, and he's got to take 2 passes when there's houses on the other side. There's houses on only one side. Okay. Okay, doesn't have to walk along here at all. Only has to take 1 pass there. Only has to take 1 pass there, and he has to take 1 pass there. Only has to take 1 pass there. Only has to take 1 pass there. Still has to walk from there to there, and from there to there. Little sloppy, but you get the gist. Draw a graph that models this street routing problem. There we go. Ooh, I'm missing an edge. So try and look and make sure that I'm not missing any edges. Okay. Now, a mail carrier must deliver mail on foot along the streets of the Green Hill subdivision shown in figure 539. His route must start and end at the post office, labeled P in the figure. The mail carrier must walk along each block twice if there are houses on both sides of the street, and once along the blocks where there are houses on only one side of the street. Find an optimal route for the mail carrier. Describe the route by labeling the edges 1, 2, 3, and so on in order in which they were traveled. Hint, you should do exercise 22 first. Ooh, I forgot a couple more. Dang. There. And there. And then my computer throws things in when it's not supposed to. And both sides of the street here. So there and there. Okay. Okay, so since we want to deliver the mail and start at the post office and end at the post office, we're looking for an Euler path. I'm sorry, an Euler circuit. We're guaranteed to have an Euler circuit as long as all our vertices are even. So after you draw your graph, then what you do is you go and look at the degree of the vertices. And so that one's even, that one's even, that one's even, that one's even. 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4, 5, 6, 7, 8. Looks like I'm still missing some. Forgot this one right here. And so then 1, 2, 3. Forgot one right there. 1, 2, 3, 4. And then 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4. 1, 2, 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, 4. 1, 2. So I've gone around and all the vertices are even. And so then we now know we have an Euler circuit. And then what you could do is go through the same process that we went to in finding an Euler circuit in the previous problem, but in the interest of time, I'm leaving that for you. That's how you set up the problem. Okay. For the graph shown in figure 620, find 3 different Hamilton circuits. Okay, so an Euler circuit is a circuit. Then we went on to chapter 6. And in chapter 6, we started doing traveling salesman problems where we weren't trying to cover all the edges. We were trying to make sure that we hit all the vertices. And so a Hamilton circuit is just a circuit that goes through all the vertices. Right, so it says find 3 different Hamilton circuits. So if it's a circuit, turns out you can start it anywhere. So we'll just start at A, all right? And then my choices starting at A is I could go to B, or I could start at A and go to J, or I could go to A and start to F. So since we're being asked to find 3 different Hamilton circuits, I'll start them here. Right? Now once I get to B, we weren't given an algorithm for this. We're just going to go from A to B, and then we'll go from B to C. And we're trying not to pass any vertice more than once. So A, B, C, right? And then we can go to D. And then we can go to H. And then we can go to G. We were not given an algorithm on how to do this. But if I do that, oh no. And then, but we just trial and error. GJ, and then I can't go to A because I'll finish the circuit and I wouldn't have visited all the vertices. I can't go to F because if I do that, then I'll have to come back to J. So instead, I go to I, and then E, and then F, and then A. Okay, so that's a Hamilton circuit. I'm not going to do all 3 of them. Hamilton, we want to visit all the vertices, not necessarily use all the edges. Using all the edges is what we do when we're doing Euler. Okay, so let's go over a Hamilton path. Same thing, Hamilton path. We want to visit all the vertices and not have a path. I'm sorry, not have a circuit. Right, so we can go from A to J because we want to end at B, so we can't go to B. And so then we come down to F, and then to E, then to I, go back up to H. Ooh, that's not going to work because then I'll get stuck. So backtrack a little bit. Huh. Okay, so again, don't make life any harder than it needs to be. We can just start at A, go take the loop that I did find and go backwards. Right, I already found one. I went from A to B. So that if I just go backwards, then I'll stop at B. So then I'll go from A to F. Then from F, I'll go to E. Then from E, I'll go to I. And then J. And then G. And then H. And then D. and then C, and then B, and then just stop there. Don't go back to A to close your circuit. Okay, and so there you go. I'm not going to do part C. You can do that one on your own. Suppose that G, B, D, C, A, F, E, and G is a Hamilton circuit in a graph. Find the number of vertices in the graph. Well, you just count the vertices right here. 1, 2, 3, 4, 5, 6, 7. There's 7 vertices. Write the Hamilton circuit using F as the starting point. Right? So then you just start at F and continue. F, E, G, and then now you're back at G, so then you go from there to B, D, C, A, and end back at F. Find 2 different Hamilton paths in the graph that start at F. So again, a Hamilton path will just not be a circuit, but it has to visit all the vertices. So if we have F, E, G, B, D, C, A, F is my circuit. I just erased the F, and now I have a path, right? And if I take it backwards, F, A, C, D, B, G, E, F, and don't write the last one, and then I have a different one. That's a different path. And they both start at F. So the motivation for Hamilton paths were these traveling salesman problems. And what we have is a graph where each edge has a weight. That is, each edge has a cost to it, and we are typically interested in finding the either the least cost, right? So, or the greatest profit. And so we have two ways of doing that. We have 3 ways of doing that. The first is called the brute force algorithm. And the brute force algorithm is just to write down all the different possible paths or circuits, and then find the cost of each one, right? And whichever one is the least cost, that's the least cost path. And so make a list of all the Hamilton circuits of the underlying graph. Calculate the total weight of each Hamilton circuit. Choose the Hamilton circuit with the least cost. Okay. So find an optimal tour for the traveling salesman problem given in figure 638 and give its cost, right? And so then you have 1, 2, 3, 4 vertices, and so then that means we have a formula for how many, since this is basically K4, then you have a formula for how many Hamilton paths you have, and that turns out to be 1 less 4 minus 1 is 3 factorial. So you have 6 different Hamilton circuits that you're going to get out of this, right? And so where does the 6 come from? Well, you can start at any edge. You can start a circuit at any vertex you want. It makes no difference. So you really don't have, we'll start them all at A, right? Now once you have, once you're going to choose them, choose A as your starting point, then you have 3 choices. So the first one, they will all start at A. But then you can either visit B, or you can visit C, or you can visit D second, right? And then once you've so then for your third one, you will then have two choices. So each column will have two choices. So you can go A, B, C, or you can go A, B, D. But once you do that, then for your last choice, you don't have for your last visit, you don't have a choice anymore. A, B, C, D. And then you're going to go back to A. And then A, B, D, then you'd have to go to C, and then you'd have to go back to A. So you have AC and AC, and then you could either go to B, or you could go to D. But if you go to B, then last you have to go to D, and then A. And if you go to D, then you'd have to go to B, and then to A. So then in your third column, they're both going to be AD, and then you could either go to B or C, and then you'd have to go back to A. And then you have AD, and if you went to C, then you would have to go to B, and then you'd have to go back to A. Now, you have 6 choices, but 3 of them are the same. So here's what you can do. Now you have circuit, cost, and then over here we have circuit. Okay, so A, B, C, D, A is the same as AD, A, B, C, D, A is the same as A, D, C, B, A. And then A, B, D, C, A is the same as AC, D, B, A. And then AC, B, D, A is the same as A, D, B, C, A. So that's that one and that one. And there we have all 6 of them accounted for. Now from A to B is 30, plus from B to C is 25, plus from C to D is 60, and then plus from D to A is 40. And so then that gives us a total cost of 30 plus 25 plus 60 plus 40, 155. ABDCA, AB 30, B to D 20, D to C 60, and then C to A 80. So 30 plus 20 plus 60 plus 80, 190. And then finally, A to C, 80. C to B, 25. And then B to D, 20. And then D to A, 40. So 80 plus 25 plus 20 plus 40, 165. And you can see that this one is the cheapest one. Find an optimal tour for the traveling salesman problem given in figure 638 and give its cost. So 165. Next, we went over the nearest neighbor algorithm. And start at the designated starting vertex. If there is no designated starting vertex, pick any vertex. From the starting vertex, go to its nearest neighbor, i.e. the vertex for which the corresponding edge has the smallest weight. Middle steps. From each vertex, go to its nearest neighbor, choosing only among the vertices that haven't yet been visited. If there is more than one nearest neighbor, choose among them at random. Keep doing this until all the vertices have been visited. From the last vertex, return to the starting vertex. The tour that we get is called the nearest neighbor tour. Okay. So, a space station is scheduled to visit the moons of Callisto, Ganymede, Io, Mimas, and Titan to collect rock samples at each and then return to Earth, E. The travel time in years are given in the weighted graph shown in figure 644. Note this is the interplanetary TSP discussed in example 611. Find the nearest neighbor tour starting with vertex E. Give the total travel time of this tour. Okay, so just like the name implies, we start at Earth and then we take the nearest neighbor, right? So we have an 8-1 here, a 3-6 here, and then a 3-1 here and a 3-2 here. So the nearest neighbor would be the 3-1. So we are going to go from E to C. Now we're at C, and we can either take the 5.6, the 0.8, the 0.52, and so then that's it. So we're going to take the 0.8. So we're going to go to I. And so then what we have is 3.1 and 0.8. Now we're at I. Can't go back to E. 3.6. We've already been there. And so then we have a 4.7 and a 5.1. Of course, we're going to take the 4.7. So we will go to Mars and we will have 4.7. Okay, and now we're here, right? Can't go back to E because we've already been there. We've got G at 5.7 and we've got T at 0.6. So of course we're going to take the 0.6 and go to T. And once we go to T, we can't go to I because we've already been there. Can't go to E, right? So we will take the 5.9 and go to G. Okay. And now we're at G. Now we're at G. And we have visited all the vertices, and we just don't have we just haven't visited. We just need to go back now, right? So we visited C, I, M, T, E, and so now then there is no vertex that we haven't been to. So now we go back to E, and that's 3.2. And so then we total those up. 3.1 plus 0.8 plus 4.7 plus 0.6 plus 5.9 plus 3.2, 18.3. 18.3 years. And there we go. Started at E, ended at E, and we have our nearest neighbor. Okay. And the next algorithm we have for finding our optimal tour is the cheapest link algorithm. And the cheapest link algorithm, we pick the cheapest link available. If there is more than one, randomly pick one among the cheapest links. Highlight the link in red or any other color. Pick the next cheapest link available and highlight it. Steps 3, 4, all the way to n minus 1. Continue picking and highlighting the cheapest available link that does not violate the partial circuit rule, i.e. does not close a partial circuit, or B, does not violate the 3-edge rule, i.e. does not create 3 edges meeting a vertex at the same vertex. So since we're looking for a Hamilton circuit, we don't want to visit any vertex more than once. And if we have a circuit other than the Hamilton circuit, then we're violating the then we're going to visit a vertex more than once. And if we have 3 edges coming out of a vertex, then we'll visit that vertex more than once. And so if you stay away from those, this is called the cheapest link algorithm. Step N, connect the 2 vertices that close the red circuit. Once we have the Hamilton circuit, we can add a direction of travel clockwise or counterclockwise. Either one gives the cheapest link tour. Okay, so a social worker starts from her home A and visits clients at B, C, D, and E in any order, and return home to A at the end of the day. The graph in figure 640 shows the distance in miles between the 5 locations. Find an optimal tour for this TSP and give its cost in miles. Hint, the edge AC is part of an optimal tour. Right, so we want to do problem 48, which is to find the cheapest link tour for the social worker TSP discussed in exercise 30. So in exercise 30, since we have 1, 2, 3, 4, 5 vertices, 5 minus 1 is 4. 4 factorial is 4 times 2, which is 8 times 3, which is 12. 4 times 8, 4 times 3 is 12, times 2 is 24. There would be 24 different circuits to go through, and that would be a lot. And so the cheapest link tour isn't going to guarantee us the optimal one, but it's a lot easier to use, and for most purposes it will be good enough. Right, so find the cheapest link tour for the social worker TSP discussed in exercise 30. And so we scan around and we look, and then we definitely want to use from A to C. Now we don't want to close any circuits, but you can see that using the edge from A to C, you can't close a circuit. So it's not until the 3rd edge that you choose that you have to be careful. First 2 edges are fine. So 4, 5, 3, 6, 3, 3, 5, 9, 3, 5, 5, 3, 5, 6, 5, 0, 6, 8. It looks like 3, 3. Okay, now now if you look, 3, 6 looks like the cheapest one. Oh no, there's a 3, 5. But we couldn't use 3, 6 anyway because it would close the circuit. We can't use 3, 5 because we'll have 3 edges coming out of there. And again, we have 5 vertices, and so then we're going to need to do this 4 times. We've already done it twice. We need 2 more. But we can't use 3, 6 or 3, 5 or 3, 6. So we move on to 4, 5, and 4, 5 does not close. And so then all I need is 1 more, right? We need to do this 4 times. So we have 5, 5, 3. Can't use 3, 5. Can't use 3, 6. 5, 5, 3. Can't use 5, 3 because it has 2 edges coming out of it. It'll have 3 edges coming out of it. 5, 9. But we don't need 5, 9 because we have a cheaper one over here. 5. So that looks like it's the cheapest one. And then finally, we need to close the circuit. And we'll close the circuit by coming in here. Now we've visited all the vertices. So we have a Hamilton circuit. Okay, so find the cheapest link tour for the social worker, TSP. So the cheapest link tour. A social worker starts from her home at A, so A, and then she can go to C, and then she can go to B, and then she can go to D, and then she can go to E, and then she'll go back to A. A to C will be 1.1. C to B will be 3.3. B to D will be 5.9. D to E will be 5.0. And then E to A will be 4.5. (1.1) plus 3.3 plus 5.9 plus 5.0 plus 4.5. 19.8 miles. Okay, so let's move on. Next we went on to chapter 7, and we talked about trees, right? So some properties of trees. In a tree, there is one and only one path joining any 2 vertices. If there is one and only one path joining any 2 vertices of a graph, then the graph must be a tree. In a tree, every edge is a bridge. If every edge of a graph is a bridge, then the graph must be a tree. A tree with n vertices has n minus 1 edges. If a network n has n vertices and n minus 1 edges, then it must be a tree. And reformulate property 3 to property 4. If a network has n vertices and m edges, then m is greater than or equal to n minus 1. For convenience, we will refer to the difference r equals m minus n minus 1 as the redundancy of the network. So n minus 1 is how many edges you absolutely need to be connected. M is how many vertices how many edges you have, and if you take the difference of the two, you'll have how many extra edges. So if m equals n minus 1, the network is a tree. If m is greater than n minus 1, the network has circuits and is not a tree. Okay, so consider the tree shown in figure 725. How many degrees of separation are there between A and P? Okay, so again, because it's a tree, there's one and only one path between any 2 vertices. So we want the degrees of separation from A to P. There's only one path. So P is over here. And if we want to get from there to here, you see we don't have to go through all the possibilities because there's only one. 1, 2, 3, 4, 5. How many degrees of separation are there between E and P? Well, again, only one path. So if we first get from E to A, 1, 2, and then we already know that from A to P is 5, so then that's 7. How many degrees of separation are there between L and P? And again, 1, 2, then we have the path, and we already had 7, so now we have 9. What is the diameter of the network? The diameter is just the largest degree of separation, and it seems like L and P are as far away as you could possibly be, and so then 9. Consider the network shown in figure 729. Find a spanning tree of the network, right? So if you notice, you have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13 vertices, and you have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 edges. So this is a tree. So find a spanning tree. The graph itself is a tree, so it is the spanning tree. Calculate the redundancy. Since it's a tree, the redundancy is 0. There aren't any extra edges. What is the diameter of the network? We've already calculated that. That was 9. It's the same problem that we had here. And so in a network, we want to find the cheapest spanning tree, the minimal spanning tree, right? And so then Kruskal's algorithm tells us how to do that. It's basically the cheapest link. So pick the cheapest link available. In case of a tie, pick one at random, mark it, say in red. Pick the next cheapest link available and mark it. Steps 3, 4, all the way to n-1. Continue picking and marking the cheapest unmarked link available that does not create a circuit. So you just don't want to create circuits, and then you're good. And so we have find the minimal spanning tree of the network shown in figure 741 using Kruskal's algorithm and give its weight. So we have 1, 2, 3, 4 vertices in this row, and we have 1, 2, 3, 4 rows. So 4 times 4 is 16. So we have 16 vertices, and since we have 16 vertices, we need 15 edges, right? And so then we just go looking for the cheapest edges that we can find. So by scanning them, it looks like 10 is the cheapest edge. And as long as we don't pick as long as we don't close a circuit, we're good. Haven't closed any circuits. No more 10s. We move on to the 15s. Can't use this 15 because it closes that circuit. I can use that 15. Now we have 20. There's that 20. There's that 20. Can't use this 20 because it closes a circuit. Okay, move on to 25. There's a 25. Can't use this 25 because it will close this circuit. We have some 30s. We can't use this 30 because it will close this circuit here. It will close this circuit right here. So I can't use that 30. Can't use this. I can use this 30. I can't use this 30 because it'll now close that circuit. I can use this 30. And I can't use that 30 because it'll close that circuit. Can't use this 35 because it'll close that circuit. And then I can use that 30. I can't use that 30. Can't use that 35. Okay. Do I have 15 edges? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. Right, I have 15 edges. It's all connected. And so there we go. That's the minimal spanning tree. Add up all the weights of the edges and you get your weight. I'll let you do that.